we can save much more. As we learn from Shirley Tarboton, she's actually on a mission to make the software greener. And our code uses a lot of energy, and sometimes it uses even more energy than you should think, actually. Shirley will talk us about writing software that's better for the environment, and with few tips, one step at a time, one function at a time, our software will become greener. So, big applause for Shirley.
Thank you. Hi everybody, I'm Shirley from the UK and really pleased to be here. Thank you for the warm welcome. And I work for a management consultancy called PA Consulting. They're based in the UK, but they have got offices here in the Netherlands and in Denmark and in many parts of Europe and the US. And I'm really pleased to have joined them because they do have a sustainable IT community. So I joined them 2 months ago, and they have some green coding standards, which is my passion. A bit more about me. Ik kan niet Nederlands praten, maar ik kan een beetje Afrikaans praten. Kan je verstaan? Yeah. Okay, where am I from? I'm from South Africa. And that's where I went to school and university, and I initially started my career as a lecturer in IT after doing my computer science degree. And then after lecturing for a few years, I moved to the UK, and that's when I moved into consulting. In 2001, I was working in consulting for a digital TV project when I fell pregnant with my son, and I ended up taking quite an extended maternity break. The dot-com bubble burst, and at the same time we were thinking about that digital divide and how to cross it. And I was interested in voice XML and got involved in the social enterprise to try and use phones to cross the digital divide. And that went well at that stage, but then smartphones came along and voice XML. I don't know if anybody ever heard of it? Oh, you have? Okay, good. Yeah, but it sort of became a bit obsolete. So I ended up taking a much longer career break to look after my kids and work in the charity sector. And then in 2012, when my daughter went off to school, I decided I wanted to get back into IT, and the opportunity was to learn Java at that stage. So I started again by learning Java, and I've been a software engineer for many years, and more recently moved into architecture. Okay, but let's get this talk in context. As many of you may know, in 2024, the average global temperature increased. The increase was more than 1.5 degrees centigrade, which is confirmed by the UK Met Office and by the European Copernicus Climate Change Service. There are still, I think, some US groups that disagree, but we know that we can all feel that things are getting warmer. We know that the demand for cloud and AI is growing, and Microsoft in their most recent report shared that their energy use has increased by 168% since 2020. So with that demand for energy growing, organizations like Google and AWS have needed to invest in their own power sources. There have been announcements in October, May, and most recently by AWS in June that they are partnering with nuclear power providers to try and meet the demand. So what can we do? Well, we can write leaner code. We can improve the way that we test that code. we can ensure that when that code scales, it does so optimally. Just going to refer again to the kind of green coding standards and some other references for the points that I just made. So writing more efficient code, what does that involve? Well, I think we all agree that elegant code is efficient because it's easy to maintain, it's easy to read, and generally it's easy to reuse. Is anybody familiar with Occam's razor? Yeah, okay. So we know that simple is generally good, and well-designed solutions that deal well with storage are going to have the smallest carbon footprint. So in general, whenever your CPU is working through something, it's using electricity, and as a result of using electricity, it will be generating carbon emissions. RAM accounts for about 25% of those carbon emissions, and I hope that Bert, when he speaks after me, will give you far more on the figures. Right, green coding best practices probably are very similar to normal coding practices. I'm going to start with one which I find particularly important, which is logging, because we don't always think about logging. In fact, on one of my most recent projects, the best practices said log copiously, which actually isn't great from a green carbon point of view, because logging's an I/O operation, it has to be stored somewhere, it has to be maintained. So yeah, I think logging thoughtfully and at the right level is important. And in fact, it's hard to debug issues when there is a lot of logging, so keeping that logging down to a minimum is good for many reasons. And if you're trying to debug code and you've got some kind of a trace condition, you might find it's harder to find that issue if you're in your dev environment, because your debugging can slow, sorry, your logging at debug level can slow your code down so much. Do you all know KISS, YAGMI, and DRY? Yeah, okay, so those definitely apply. We don't want anything redundant if we don't need it. And then talking about querying, we're having a conversation over lunchtime today with some of the other speakers about how we really want to push queries down to the lowest level. So you don't want to be passing all of that back-end data to the front end if it's not needed. Just try and filter as low as you can. Using lazy loading and caching results will also mean that there are less storage requests, which means that you're going to be burning less coal and generating less carbon emissions if you're in a country which has some coal on the grid. And another point for more front-end developers is to try and design for low bandwidth users, so that you're using low resolution images and potentially video resources, any kind of resources where you can, by default, minimize the impact. I'm just going to work now through an example of an algorithm. So I'm sure everybody who's coded will have come across sorting algorithms, and I've got two versions of quicksort here. The one on the left is pretty standard. In fact, it's off the wiki page. And the one on the right was generated by Copilot. And the one on the right does look a lot more elegant. It's much shorter. However, although they are both big O notation, order, n log n in terms of CPU, the one on the left is sorting within the array. So if you have a look at the bit of code that's green, in the green box, that's sorting within the array. So that's order n. Whereas the code on the right is recursively generating new arrays and sorting within those new arrays. So the memory being used there is of the order of n squared. So although it looks like it's got a minimal carbon footprint, in fact, when you consider it, it hasn't. Oh, and by the way, yeah, the prompt that generated that was, can you write me an example of a well-optimized quicksort algorithm? So, something about AI. Okay, let's move on to unit testing. So unit testing, if we talk about coding, testing, deploying, scaling, testing is the next thing to tackle. And the pyramid on the right is the green pyramid, and it's a traditional testing pyramid. And it's green because you have lots of unit tests at the lowest level, and that's where resources are really cheap. Whereas the integration tests require that you spin up a context, and that is definitely more resource intensive, and end-to-end tests require a whole environment. So the amount of energy that's used in end-to-end testing is much higher. Now, I've been on projects where the team lead has said, don't really worry about writing lots of unit tests because the QA team are going to pick up all the issues anyway. So leave it to them and or write more in end-to-end tests. And that's the upside down pyramid. And it's not a good idea for many reasons because it just means that the loop of fixing things is so much slower, as well as the environmental cost. And there are white papers that suggest that as well. So I think it's not a green approach. Anybody disagree? Okay, something to chat about later. So what are low carbon testing practices? Well, if you're working with cloud, it's pretty easy to spin up an ephemeral test environment. It's also very easy to spin up other environments that get stale, but if they are always on, if you've generated test environments for all your teams that are running 24/7, that's going to be taking up a lot of energy that's not needed. So if you've got testing that you want to do, it's a good idea to do it in an ephemeral environment. You can use it using GitHub action runners. You could use Docker containers in test pipelines. You could use serverless test functions. Basically, you only want to consume compute when you need it. You just want to avoid over-testing and monitor what you're doing. Also, test results. If you could get rid of those, then you're freeing up the storage. Here's an example of 2 bits of code. Seen, again, a long time ago now, but this code on the left is using a thread to sleep, which is not good practice. Much better to use a utility that waits until something is completed. And here's another example of something high carbon and low carbon. So having a step in your pipeline which checks whether your commit is just pushing things like readmes and documentation could mean that your pipeline, you could make sure that you only run your testing steps when you're pushing a genuine code change. Any questions? Yeah.
High carbon example you show here.
Yeah.
I think it's still relatively green because it just tests the main branch and not every other branch.
True. Yeah. So, yeah. It's illustrative purposes. Okay. I'm going to talk now about building and deployments. So I'll just talk about building a little bit, which is an opportunity for us to try and reduce the carbon footprint of what we're going to deploy by building in a way that's minimal. What you could use is you could use a native image. Now, building to a native image can be done by using something like GraalVM. So Oracle's GraalVM will take all the extra libraries that you've got and cut those out so that what you're deploying is a much smaller image. And that means not only will it use less memory, but response times and startup times are much faster. So that is highly recommended. However, the compilation itself is very slow and memory intensive and resource intensive. So if you're going to introduce something like GraalVM, you might want to consider about when you use it. Is anybody here using native images? Yeah? Anyone? Yeah, okay, cool. So what I've heard from people who are using native images is they're using it when they've got massive peaks in scale required. Say, for example, there's a tax deadline and everybody submits their tax returns at the last minute. There's a sudden peak in requirements and Being able to scale up quickly is important, and having those images as small as possible is really important to try and minimize the amount of energy that's used and the carbon emissions as a result. So pushing that compile stage very close to when you're going into production is a way to produce a native image which isn't going to slow down all of your pipelines, because it's an intensive process. You don't want to be doing it on every single commit. Okay, so that was native images. And then just talking about provisioning. So how many of you are working with projects in the cloud? Yeah, a lot of people. And what that is, it does enable you to take advantage of cloud credentials, green credentials. So they are trying to use as much renewable energy as they can. However, when you're deploying, you may want to think carefully about the instance sizes that you're using and make sure you right sizing. So I have seen on previous projects services running with instances that were way over provisioned for the requirements. So you could have a look at the amount of CPU and memory that was being used, and it was around, for one of the services, 25% or lower. And that's clearly quite wasteful. Having multiple images, multiple containers running with minimal use. So obviously you want to have redundancy by running across different availability zones in the cloud, so you've got more resilience. But I think you can right-size those images. On the other side of that, I've seen services where the images weren't very well sized because there were constant issues with memory. There would be quite frequent tasks failing over as a result of running out of memory. And in order to address that, they'd used more and more instances, and the JVM was quite small. So they increased the size of the JVM, and that didn't solve the problem. And what was happening, it was an image-intensive process. And those images were being uploaded and decompressed and rotated, and the amount of memory that was being used was very large outside of the JVM heap. So what they needed to do was increase the container size so that the images would be able to be processed within the same instance, but with a bigger task and container size. So right-sizing in that situation meant increasing the size of the instance, but that meant they had more capacity. And so what they found that they could do is they could do more vertical scaling rather than horizontal scaling. So with vertical scaling, you're putting more onto each of the instances rather than just scaling horizontally. And that solved some of their problems. Okay, so scaling to save carbon. You would ideally like to be scaling up your services when the service is needed. So if you're an organization running during business hours, then when you need to scale up is obviously during business hours, and you could either use scheduled scaling to bring your service down, or you could use dynamic scaling. And dynamic auto-scaling can be quite difficult to implement depending on how virtualized your infrastructure is, but it's obviously going to be good from a green point of view. And then there's serverless, which is able to scale to 0, so an ideal situation. Another thing to look at about green architecture is using content delivery networks. So by caching traffic at the edge rather than having all the traffic crashing in on the center where the original content is stored, enables quite a bit of energy to be saved and therefore less carbon produced. And there's some stats there on the screen. One of the issues I think people have is my last kind of topic, and that is decommissioning. Yes, so do you feel confident once you're not using a service anymore to get rid of it? How do you go about doing it? And just thinking through the steps, if you do want to turn something off, how do you turn it off safely? How do you make sure that all your traffic is going somewhere, that you're not going to get alarms going off, that you keep a cooling period so that you monitor what's going on, that you've handled the data that you've collected properly. And then finally, once you're confident that you've got all of those things under control, removing all the components and the environments and archiving. That's something that it's worth tackling, because having environments and services hanging around that you're not using is a waste of energy. Right, so just onto my key takeaways. If you can write more elegant and optimal code, great. Don't forget to consider the big O notation of what you're writing. Test with a green pyramid. Deploy on instances that are right-sized according to your process needs. Scale dynamically. Decommission when you don't need it. And try to make sure your team is abiding by some sort of green coding standards. And there is quite a growing body of literature that you can apply, and there's training. So, my final point is just embrace the joy of writing green code. Okay.
Thank you very much. We've learned a lot, and I promise we will write a better software to save the world.
Okay, thank you.